Okay, so we have just derived the arc length formulas, and now let's do a couple examples. So here, just a restatement of the two arc length formulas. So we can either use the first one if we're given a function of x, or the second one if we're given a function of y. So let's take a look. If we were to have this example, y equals the natural log of the secant of x from x equals 0 to x equals pi over 4. We can clearly see here that this is given y as a function of x. I grabbed this little graph in Desmos, and we can see here on the graph, this right here is y equals the natural log of the secant of x from 0 to pi over 4. So if we were to want to compute the actual arc length, so the length of this curve from 0 to pi over 4, we can use our arc length formula. So let's go ahead and get started. If we're going to use the arc length formula, we need dy dx. So let's get started with that. The derivative of the natural log of the secant of x, 1 over the secant of x, times the derivative of the secant of x times the tangent of x, and then conveniently the secants cancel, and dy dx is just the tangent of x. And since we're going to have 1 plus dy dx squared, let's go ahead and do that before we pop it back into the interval. So 1 plus dy dx squared would be 1 plus the tangent squared of x. It's not that important to do that here, but it does make a little more sense for ones where we're going to have some algebra to compute. So let's go ahead. Now we can take that and we can put that into the integral. So the integral, the arc length, on x equals 0 to x equals pi over 4 is going to be equal to the integral from 0 to pi over 4 of the square root of 1 plus the tangent squared of x with respect to x. And now that is very convenient because 1 plus the tangent squared of x is just secant squared of x. Just use our identities. Worked out convenient for us there. So this is now the integral from 0 to pi over 4 square root of the secant squared of x dx, which is perfect square integral from 0 to pi over 4 of the absolute value of the secant of x dx. But notice here that we're looking at this just from 0 to pi over 4, so we can actually drop those absolute values. The secant is always positive on the interval from 0 to pi over 4. So we can go ahead and drop the absolute value and look at just the integral from 0 to pi over 4 of the secant of x dx. And of course, that's one of our useful integrals, so that's the natural log of the absolute value of the secant of x plus the tangent of x, evaluated from 0 to pi over 4. And finishing this out, I'm going to come over here just so I have a little more space. So that's the natural log of the absolute value of the secant of pi over 4 plus the tangent of pi over 4 minus the natural log of the absolute value of the secant of 0 plus the tangent of 0. And the secant of pi over 4 is just root 2, because the cosine would be root 2 over 2 or 1 over root 2. And so the secant is just root 2 plus the tangent of pi over 4 is 1, and minus, well, the natural log of this over here, the secant of 0 is 1, and the tangent of 0 is 0. So we end up with natural log of the absolute value of 1, which of course is itself 0, and our answer is the natural log of the absolute value of the square root of 2 plus 1. And that gives us the actual arc length of that original curve. So if we were to actually measure the length of the curve, it would be the natural log of root 2 plus 1. I can actually drop my absolute values. These are both positive values, so if we wanted to, let's just make those parentheses instead of absolute values. And there's our final answer.